Hello everyone, I'm Adam. For our function here, which we have f of xy equals to x squared plus y squared plus 8x minus 12y minus 3, we're going to find all relative extrema and saddle points, and if we can, we're going to use our second partials test if it's applicable. So we want to find our relative extrema and saddle points. Now we're going to start pretty much like we would in a basic calculus course, is we're going to find our candidate points, and those occur at the critical points. So how we start by finding those is we're going to look at our first order partial derivatives with respect to x and y. Right. So we're going to look at the first order partial derivative of f with respect to x, and we take a look at that, and we're going to have, say, 2x plus 8, and the first order partial derivative of f with respect to y, we'll have, say, 2y minus 12. Now, to find the critical points, those are going to be points where our partial derivatives here are either equal to 0 or undefined. Now, we can see that our partial derivatives are linear, so they're not going to be undefined, so we'll go ahead and see where they're equal to 0. So we'll take our 2x plus 8, set that equal to 0, and solve, and our 2y minus 12, and set that equal to 0 and solve for it. So 2x plus 8 equal to 0, subtracting 8 and dividing by 2, we'll get x equal to negative 4. And for 2y minus 12 equal to 0, adding 12 dividing by 2, we'll get y is equal to positive 6. So that tells us, right, so we're going to have a critical point here at x equals negative 4 and y equals positive 6. Now what can we do from here? Well, if we think for a second, we've actually met one of the beginning conditions of the second partials test, and that is to have a point such that at our first order partial derivatives with respect to x and y, they're equal to 0. Now the other condition is that all the second partial derivatives are continuous on some open region containing this point. So it won't take too much work, but we'll go ahead and check that out to see if we can use the second partials test. So we'll look at our second order, say, partial derivative of f with respect to x. And so looking up here at our first order partial derivative, is going to be equal to, say, 2. And the second order partial derivative of f with respect to y is also going to be equal to just 2. And our mixed partial derivatives, derivative of f with respect to x and y, partial derivative, that is just going to, looking at our first order partial derivative with respect to x, then taking the derivative of 2x plus 8 with respect to y is going to be 0. And the mixed partial with respect to y and x, looking at our first partial derivative with respect to y, taking the derivative of 2y minus 12 with respect to x would also give us 0. So what do we have? All our second order partial derivatives are constants, so meaning they're going to be continuous functions, particularly around our critical point. So we can use the second partials test. So what do we need to find now? Well, with our second partials test, we're going to need to compute this quantity, say d, which is the second order partial derivative with respect to x, with our evaluated at our critical point, so negative 4, 6, and then times the second order partial derivative of f with respect to y, also evaluated at the critical point, and then minus the mixed partial derivative f of xy evaluated also at our critical point, and that quantity squared. So we're going to compute this value and see what we can do with it. So being that all our second partial derivatives were constants, so second partial derivative with respect to x was 2, so even if we plug in the points negative 4 and 6, we'll just have the constant 2. Likewise, for our second order partial derivative with respect to y, evaluated at our critical point is just 2, and then minus, right, the constant, which would just be 0 squared. So it looks like our value d is equal to 4. Now what can we do with that? Well, according to our second partials test, since the value of d we've computed, which is equal to 4, but namely is positive, and the second order partial derivative with respect to x evaluated at our critical point, which was equal to 2, is positive, then we can say that our function f has a relative minimum, right, at our critical point, -4, 6, by our second partials test. Now let's take these coordinates and plug them back into our original equation to see if we can find the minimum height or z value. So let's look at, say, f of -4 and 6. So we'll have this equal to -4 squared plus 6 squared plus 8 times -4 minus 12 times 6 minus 3. And computing all this, we get a value of say, 55. So our relative minimum value is -55. So there we go. Thank you very much.